Great. So first, before we go to the things that we want to discuss today, some of you wrote me with problems you found while you were trying to get the mean field limit of the two species model we worked yesterday with. I hope I solved all of them. If I didn't, you can write me back, or if any of you have more. But and now I forgot. Sorry, I forgot the name of the person. But well, one of you pointed to some Pedro. Yes, sorry. To some typo in my notes. So thanks a lot, Pedro. Very quickly, so you don't get confused with my bad notation. I told you yesterday, as I was explaining this, that I am always messing things up with the notation. So here I'm saying that gamma ij means that j inhibits the growth of I. And then I said that I was going to say that the white species was 1 and the pink was 2. I don't know, black is probably not the best color to use. So this was 2 and this was 1. So basically the notation here is incorrect, because here the pink is, sorry. Yes, exactly. Here the white is inhibiting the growth, sorry. Here the white is inhibiting the growth of the pink, because the one that disappears is the pink. So this should be gamma 2, 1, and this should be gamma 1, 2. So whenever you write your master equations, this should appear in that order, not in the one that I made yesterday. So anyway, that was it for yesterday. Today, as we said very briefly yesterday, and let me remove. As we said very briefly yesterday, today we have 2 goals. One is going to be more mathematical, so maybe more fun for those of you that are more in the math side. And the other one is going to be, how I did this yesterday. I did something like this, I think. And the other one is going to be a bit less mathematical, more intuitive, more about drawing dynamics and getting ideas from a graphical analysis. So 2 parts. And because there are many things to do, I'm going to move to explaining the first one. So as I said, in this first part, we are going to do a calculation that I left unfinished yesterday. That is basically the linear stability analysis in 2D. So we want to know in these models with 2 species when I'm going to have a stable fixed point, a stable node, when I am going to have a saddle point like the one that we saw yesterday that has one direction that is attractive, the one that is repulsive. Also, Jayme asked us about the oscillations. So we want to know when we will have oscillations, if these oscillations are going to be sustained in time, or if they are going to disappear, if they are going to be damped oscillations. So we want to know how many different behaviors we can have at least around these fixed points, and how can we get them in a very systematic way. So I am going to do that using a very general system. I'm going to forget a little bit about the specific equations that we had yesterday. I am sorry, but I'm still going to use U1 and U2 as variables. And we are going to use a system that I can write in a general way like this. This is just the generalization of what we wrote yesterday. This F1, in the case of the models we had yesterday, is this U1 times 1 minus U1 minus A12 U2, if you remember, or it can be any function in general that we want. Okay, that's the idea. So of course, F1 and F2 need to be nonlinear functions because we are working with nonlinear dynamical systems. And in general, we are going to study the stability of this system around a fixed point that is going to be U1 star, U2 star. This is going to be the general way for us to write a fixed point. And the question that we now have is the stability of this point. Or in a more general way, if you want to look into the question in a different way, we want to know the behavior of the system around this point, if you don't want to use the jargon of dynamical systems. So how is the population going to behave when we are nearby that point? So I guess that many of you are already thinking that a kind of direct way to do this is basically by extending the one-dimensional case that we already did. And then the only thing we have to do is to say, okay, I'm going to work with a general solution that is made by my stationary state plus some small perturbation. And I'm going to work the same for U2. Where remember, epsilon is much smaller than 1. So again, now the only thing is that I am going to kick my solution from the fixed point a little bit. Then the only thing I have to do is I can expand, the Taylor expansion I did for the f function in the one-dimensional case, I can do it for f1 and for f2, basically. So for those of you that are already familiar with Taylor expansions in more than one dimension, this is kind of a straightforward Taylor expansion of the nonlinear functions. So you see that the math so far is not very tricky, but it will get a little bit more subtle in a while. So this is basically the F1 evaluated in U1 star plus epsilon X and evaluated in U2 star plus epsilon Y. And now I have to do a Taylor expansion of this function that I can write it here. So this would be F1 in U1 star, U2 star plus epsilon X, the derivative of F1 with respect to U1 evaluated in U1 equal to U1 star and U2 equal to U2 star plus epsilon Y, the derivative of F1 with respect to U2 evaluated in U1 U2 plus orders terms that are going to be order quadratic either in X or Y or if you want, sorry, because I have different notation here, terms that are of quadratic order in epsilon. That's the correct way to write this. So those of you that are not familiar with Taylor expansions in 2 dimensions, who are probably the ones that don't have background in math or physics, this is just the generalization of having a function in one point and moving to the right a little bit or to the left a little bit to moving in a 2-dimensional plane. I have to calculate the derivatives with respect to all the variables, but it's not something very complicated. So now again, of course, what I have now is that this is 0 because this is the definition of a fixed point. F1 in the fixed point has to be equal to 0. And now if I substitute this in my equation for U1, that I hope we all agree that I can already write it this way because the derivative of the fixed point is equal to 0, right? I am just using that U1 is equal to U1 star plus epsilon X and the derivative of this part is 0. This is going to be equal to epsilon X F1 with respect to U1. And let me say, use this abbreviation to say that I am evaluating U1 and U2 in the fixed points. Okay, this is not, I don't want to mess things a little bit and confuse you with details. So if I repeat the same for the second equation, I am guessing that, and I think I can remove this. I don't know why I put this here. I think that unsurprisingly for everyone, what I will get is basically the same, more or less the same. So the only thing I've done here is to linearize my system. A Taylor expansion truncating in the first order, now I have a linear system. And because I now have a linear system, I can write it in a matrix form, which is what I am looking for the rest of the discussion. So basically now what I have, I can write, for those of you that are not very used to the matrix notation, I have I can write it this way. This is 1, this is 2. This is evaluated always in the fixed point times x, y, and this is, sorry, derivative with respect to time. So what's the first interesting thing that we have is that this matrix here is what is called the Jacobian. So basically it's a matrix where I put the first derivatives of my nonlinear functions, right? And I have all the information about the stability of the system will be in this matrix. This is going to be the equivalent, the 2D equivalent, if we want, to this f prime of u star that we had for the logistic growth. So remember, in the case of the logistic growth, if the derivative was positive, the perturbation was growing up. If it was negative, it was decaying, stability and non-stability, or the other way around, non-stability and stability. Now, of course, I don't have the same criteria because now I have a matrix. So what we want to know now is how can we work with this matrix. I am going to skip a little bit of the details, and I'm trying to build intuition in you rather than following all the details very carefully. If you are interested in all the details, this Steven Strogat's book that we've been mentioning many times is very, very clear on that. But I think the amount of detail that I'm going to give, even if I don't open all the calculations very deeply, are going to allow you to follow all this technique, or to understand at least the technique and be able to study it by your own. So again, what we have now is something like this. Let me write it. Again, where A is this 2 times 2 matrix, X is the vector, and then I have the time derivative. So in principle, this A matrix is going to have 4 components, 4 numbers. It's made by 4 numbers that are different from each other, the value of the derivatives. I want to first take an example where A has this shape. Okay, this is equivalent, or the other way around, sorry. I'm not going to even write the yes, sorry, let's take this one. So in this case, what is interesting about this case is that the systems, the dynamics in each of the dimensions is decoupled. So if I have my system that is this way, basically I can write the solutions like xt is equal to some, let's say x0 e or f of t, and I of t is equal to I0 e t. Okay, this is a particular case where I can solve my dynamics and I have this kind of solutions. Why I am interested in this type of solutions? Because now if I go to the phase space that we drew yesterday, the dynamics in each of the dimensions is independent from each other. So I can study them differently. So for instance, imagine that I ask you now, what is the long-term behavior of this system? If t goes to infinity, what is the long-term behavior of this system? Of course, the fixed point. Let's go, which one is going to be the fixed point of this? where does this solution go when t goes to infinity? To 0, 0, right? Both the dynamics in x and in y, they go to 0. So this is my fixed point. But now, because of this decoupling, I can build a lot of intuition. And please let me if this is not clear for any of you. If A, let's take the easiest case. A is going to be equal to -1. This means that the solution in x and the solution in y are identical. So then when t goes to infinity, I will always approach the fixed point in a direction where the both components x and y have the same velocity.
Ricardo?
Yes.
The A that you defined in the matrix is already negative. So I guess you're talking about the case in which A equal 1.
Because I put a minus here. Sorry. So let's put this. Okay. Is that right?
So in the equation, we don't have the minus in the x of t equation then.
Exactly.
Right?
Exactly. Perfect. Thank you. You see, one more. So when the idea is that when A is equal to -1, the x and y, the dynamics and in x and y have the same direction, and then I should approach this way. If this is not clear for everyone, let me give you now another example, and let's see what do you guys think. How do you guys think the solution is going to approach the fixed point? We are going to consider now, sorry, let's make this a bit more clear. This would be A equal to -1. And let's consider here a case where A is smaller than -1. When t goes to infinity, or let me make the question the other way. Which of these solutions goes to 0 faster? X or Y? One decays like the exponential of -t, and the other one like the exponential of something that is more negative than -1. So which one decays faster?
X.
X decays faster, everyone agrees with that? Okay, so then when the time goes to infinity, the movement in x is already 0, right? And I could in principle think that the movement has to be in the direction of y. So I should approach the point in a way that in the very last minutes of my dynamics, I am also tangential, I am almost tangential to the y-axis. Right? But now I can revert the order. I can tell you, but what happens when time is very small? Which is the direction that dominates when time is very small? X or Y?
Y.
Y also? Why?
This was a question. I don't know why is the letter or why the question.
Ah, sorry. You are someone. I think you answer why, and I am asking.
I answer why. Yeah.
And I ask, and I am asking why. Why do you say is why? So why do you think that if I go for a very time, if I go a lot into the past, why do you think that the direction that dominates should be this one?
Now I'm thinking.
X, we have a lot of X. Someone saying X in the chat wants to say why. I'm going to ask the question in a different way to see if that helps. Can we consider that the very much into the past is equivalent to saying that time goes to minus infinity? If I go to time, if I take time going to minus infinity, then which is the direction that should dominate? The one with a smaller decay rate, right?
Yes.
So in principle, when time is very, very much into the past, I have something like this. So I can sketch my kind of trajectories by putting these pieces together, saying that this is kind of the kind of dynamics that I would get from this case. And guys, as I said before, you can work all these cases with A between 0 and -1, and you can see how you will get these different trajectories, and you can play around generating this intuition and see how it works. But this is for a very, very specific case, right? This is for a case where I have a dynamics that is decoupled. But the reason why I wanted to discuss it first is because now, when we are going to go to dxt equal to A times X, in general, I can propose, and now I'm not being very rigorous. So those of you that are really mathematically rigorous can read the proper arguments in the book if you want, and we can discuss them. I can kind of hypothesize that my solutions are going to be something like this, like a linear combination of exponential solutions. In principle, I have a linear system, and I can say, okay, my solution can be a linear combination of these exponentials, and something that I already learned from this example, that is the reason why I wanted to discuss it first, is that wherever these V directions are going to be the directions that dominate in the long term and in the super past and in the super future, no? The time going to -infinity and to +infinity. So, and finally, these lambdas are going to be some kind of decay rate of the dynamics in these directions. Okay, that's the intuitive idea. So what I can do is I can just plug this solution into my equation, like a kind of ansatz solution for those of you that are more mathematical. So basically, the derivative of x with respect to t is going to be lambda e to the power of lambda t times v, and this is going to be equal to a e lambda t v. This can cancel because this is just I'm sorry, a scalar, and this is what I get. What is this? Apart from an equation written without a vector. What is this? Sorry, someone was going to speak and I interrupted.
I don't know how to speak in English, but autovalor, autovetor, eigenvalue.
Exactamente, eigenvalue and eigenvector. So basically, sorry, basically these V vectors here are going to be the eigenvectors of my Jacobian matrix, and lambda are going to be the eigenvalues of my Jacobian matrix. And remember that the eigenvectors of my Jacobian matrix are going to give me, the eigenvectors are going to give me these privileged directions of motion. Privilege in the sense of the ones that dominate at different time limits, and lambda, the eigenvalues, are going to give me the stability of those directions, whether the dynamics in that direction exploits or not. So all my problem now reduces to calculating these eigenvalues and these eigenvectors. So this is an algebraic, this is something that those of you that have taken algebra or linear algebra know how to do it. I am just going to go very fast through the steps so we can get to the conclusions and we don't run very late on time. So basically, if you guys want to calculate, if you have a matrix, that remember now it's a general matrix A, B, C, D, and you want to calculate these eigenvectors and eigenvalues, then what you have to do is to go with a characteristic equation. You basically have to solve the determinant of A minus lambda B C D minus lambda equal to 0. So you have to solve this determinant. Many of you probably know how to do it. Basically, if you do some simplifications on some algebra, after expanding this determinant, what you will get is that lambda squared minus the trace of A lambda plus the determinant of A is going to be equal to 0. So you are going to obtain your lambda from the roots of this equation. And basically the trace of A, for those of you that are not very familiar with algebra, the trace of A is the sum of the diagonal elements and the determinant of, let me try to make some room. This is the only thing I like about the tablet more than about the Blackboard, that I don't have to delete. And then the determinant of A is equal to AD minus B. See, this is a clear example of dyslexia. Right, so this is what I have. And I can keep on, I mean, the trace and the determinant are just numbers, so I can keep solving my equation, and I will get that I have two eigenvalues that are going to be lambda 1, 2, are going to be the trace of A plus minus trace of A squared minus 4 dt, determinant of A divided by 2A, which is 2. So these are my two eigenvalues. Depending on the trace and the determinant of the Jacobian matrix, these eigenvalues can be real, they can be complex, they can be pure imaginary, they can be many different things. I will invite you to explore the different possibilities. I'm going to sketch here for you how you order these eigenvalues and how you get the different behaviors depending on the values of the trace and the determinant. But basically, I'm going to give you some intuition. For instance, you can say, okay, if the determinant of the matrix is negative, if the determinant of the matrix is negative, then everything here is going to be positive, so my eigenvalues are going to be real. And if this, of course, because this inside the matrix is going to be, sorry, this inside the square root is going to be larger than the trace of A, right? Because I am adding some other number here. Then I know that the eigenvalues are both going to be real, and one is going to be positive, and the other one is going to be negative, because I have the trace of A, and I am adding to it a number that is larger than the trace of A, or I am subtracting a number that is smaller than the trace of A. So I can organize, and you can, I will share with you an actual industrial production of this plot, so it's more clear. I don't know if industrial is the word, but a professional making of this plot. But basically what I can say is, okay, I'm going to put in this axis here the trace of A. And here I'm going to put the determinant of A. So we said if the determinant of A is negative, I would be in this part here. Then my eigenvalues are going to be both real and with different signs. So one is going to be positive and the other one is going to be negative. In this case, guys, what you are going to have is one of these, it's called saddle nodes. One of these saddle nodes that we found, for instance, yesterday in the Lot-Volterra competitive model. So basically, we are going to have a direction that I am going to use it as X and Y, but in general, it's going to be different. I have one direction that is going to be repulsive. I have one direction that is going to be attractive. And basically, my trajectories are going to look like this, as we saw yesterday. Or as we saw in the previous example also, when A was smaller than -1. So you can repeat this this for different. You can solve the square root, and you will see that if the determinant is positive, there will be a line here that will be given by the trace of A square. I think it's, I may be making something wrong, but I think it's the trace of A square minus 4, the determinant of A. Right? And if we are inside this parabola, our eigenvalues will have some some imaginary component. They are not going to be, they are going to be complex, and they are going to be complex conjugate. Okay? And in this case, I am telling you, depending on the value of the trace, we are going to have a dynamics that is going to be a spiral that goes away from the fixed point, or we are going to have a spiral that goes towards the fixed point. If the trace is equal to 0 in this, let's say, I don't know if problematic is the word, but in this case, degenerate case, what we have is we're going to have eigenvalues that are purely imaginary, right? We are here where the trace is 0, so I don't have this part, and I will have the square root of a negative number. In this case, what we have is a dynamics in which the populations oscillate, or the variables oscillate around the fixed point without never touching it. So in this case, we do have sustained oscillations in time. Whereas in this case, we do have oscillations that go damped towards the fixed point. Again, I'm being very qualitative. I am skipping a lot of details, but it's because I don't want to focus a lot on this mathematical part. I think with these details, you guys basically get a recipe to evaluate the stability of these fixed points, and to get to see the type of fixed points that you expect in these models. Just a final note before I open it for questions, why I know that given these eigenvalues, I get all these different sorts of dynamics, because remember that we were saying that our solutions, we use ansatz that are like this. And these directions V are fixed in time. So basically what we have is some linear combination of exponential solutions, right? So if both my, for instance, let's take the case that maybe is less intuitive. If my lambdas are imaginary, this is a linear combination of sinus and cosinus, right? So then what I have is oscillatory solutions. If they are complex conjugates, then this is an exponential. This is an exponential of this type, right? If lambda 1 is a complex number, and then this is this way. So basically, I have a real part in my eigenvalue, and I have an imaginary part. So I have oscillations, and I have an exponential either decay. If alpha is negative, it's a decay, and if alpha is positive, it's an exponential growth that is going to tell me that I move away from the fixed point. So the exponential, instead of being damping my solution, is making the amplitude of the oscillations to increase, and my solution to diverge. It's kind of an unstable spiral. The other one is an unstable spiral. So I hope this explanation didn't lie in the point where I give details for you to get an idea, but so I hope I didn't stay in the point where I confuse you rather than illuminate you. But if I did, please ask me, and I'm happy to take some more time explaining this and maybe being faster in the second part. So if you have questions, please go for them. I think those of you with strong physics background could, or at least get an idea. If you don't have that background, please ask and I can open details more.
Ricardo,
Yes.
a small detail. I think the blue line would be the trace squared minus 4 the determinant equals 0.
Of course. Of course. Yes. Thank you, Rafael. And in this case, I can, so in case you guys want to complete, in this, I can call this delta, and in this case, delta would be positive, and in this case, delta would be negative. Yes, very important detail. Thanks, Rafael. Amanda.
Ricardo, just one silly question for that specific case that you showed when the trace it's equal to 0. So if we try to think about ecological systems, that would mean that either we have no intra-specific interaction, or we have like inverter signals for the two populations, like +6 in one and -6 in the other. So when you sum, it will.
Yes, so that's, for instance, the traditional Lotka-Volterra model, pre-predator Lotka-Volterra model. It does have oscillations. Why? Because they discard the intraspecific interactions. They only say, I have exponential growth in the price. I can write it for you guys. It's probably the only equations I know by heart. And now that I said this, I will probably write them wrong. But for those of you guys that don't know the model so well, the Lotka-Volterra pre-predator model, that is the one that I showed you yesterday, the oscillations. If X is the prey, then the change in X is equal to some exponential growth of the prey and some consumption by the predator, and then the predator dies at a constant rate and grows only when there are preys. And in principle, gamma can be different to beta. I think these are the questions. But the idea is precisely that, Amanda, you don't have interspecific competition. So then the trace is going to be 0 and you have oscillations. There are a lot of people studying, especially mostly mathematicians, studying this model with logistic growth here. And then they show, of course, now I don't have oscillations anymore, or I have these behaviors, because basically you are changing the properties of the matrix. And here I should have.
Thank you.
Thank you. More questions? No? Okay, so then I think we can move to the second part, which I already anticipate you guys is going to be less mathematical and more about intuition and plots. So this second part is what I told you the first day. We're going to study discrete in time models. So why are these models meaningful? I'm not just going to say important, but why are they meaningful? So we said when we were studying these models that gave us differential equations, at the end we were saying we have these cells that die at a constant rate, they have a probability per unit time of dying, and eventually everything was happening at constant time, in continuous time, sorry. Every time I could be seeing something. That happens for many, many systems and many, many organisms, but there are other organisms that don't follow this reproduction, this reproductive pattern. For instance, we have some insects that only reproduce 1 per year or twice per year, and they do that in an amazingly synchronized way. They have like the reproductive time and they reproduce. There is other insects, for instance, if you want to check them out, it happened this year. It was very, very fascinating. I think there were crickets. In Spanish is cigarra, and I think in Portuguese is cigarra as well, but you can correct me, that they spend 17 years underground fitting in roots, and every 17 years they hatch. They go outside and they make a crazy sound, and YouTube is full of videos with that. Every 17 years, there are a lot of studies saying why 17, and it seems to me that there is something behind the 17 being a prime number, and that is not coupled with many other life cycles, so that enhances their probabilities of survival. There are cases that are way less extreme. For instance, bamboo, they flower once every 1 year, 3 years, depending on the species, but they have very well synchronized life cycles. For those cases, of course, we can take a different approach to the one that we have taken so far, and we can discretize time, and we can think of time in terms of generations. So we can say that one generation does not overlap with the previous generation, which is, for instance, that doesn't happen in humans. In humans, luckily for many of us, we are lucky enough to overlap with 1, 2, and those of you that are especially lucky with 3 generations of either predecessors or descendants. That depends on every. But we have overlapping generations. Some insects don't. And in those cases, we describe the dynamics of these systems instead of with differential equations, with difference equations. Basically, we are going to reproduce to model the reproduction of these populations following an iteration process. We are going to iterate over the number of species and over the number of individuals, and we are going to see how that population either grows or that population declines. I can tell you that despite this seems to be easier, discrete in time models, difference equations are way more complex and way more hard to deal with analytically than differential equations. That might be disappointing, but it is also good because that means that we need to develop tools that are more fun to do, like plots, graphic analysis, computer simulations. So for those of you that don't like spending time with the paper and breaking your brains, it's a good news in everything. But the problem is the one that we always have. We don't have analytical tools, that it is hard to get general laws about the behavior of the system. So jokes apart, is a problem rather than an advantage. So we are going to study 3 different types of reproduction. We're going to study what we are going to call density-independent reproduction, and we're going to explain each of them very carefully. We're going to study what I'm going to call compensation, and we are going to study overcompensation. This is just names so far, compensation. So the easiest one, number 1, is going to be never be left-handed. It's a problem for everything in life. I always put my hand in the button to go back to the menu, and I lost the blackboard. Density independent. So what does it mean, density independent? Density independent means that I produce the same number of offspring regardless of how many individuals are in the population. Every generation, every individual leaves behind 2 offspring, 3 offspring, 5, 1.2. Why 1.2? Because we are going to talk about mean number of offspring. So I don't know, some people or some insects will leave 2, some insects will leave 1. In average, they can leave 1.2. So in principle, if I say that the number of individuals at time t plus 1 is equal to R0 times the number of individuals at time t, this R0 can be a real number. It doesn't need to be integer, it doesn't need to be positive, because if the number of offspring that we leave behind in average is smaller than it doesn't need to be larger than 1. That's what I mean. If it's smaller than 1, then the population will tend to decrease. So this is the most simple difference equation we can write, the most simple discrete in time model that we can write. We can evaluate it very easily. For instance, we can say that if we start with some n0 individual, this is the initial population size, then I just come to my difference equation, to my iteration rule, and I say, okay, so now n1 is going to be R0, n0. n2 is going to be R0, n1. Or in other words, it's going to be R0 times R0 and 0. And we can iterate this map many times. As you go forward in time, you will get that nt is equal to R0 to the power of t, and 0. So something that is already coming up here is that the when we assume this discrete time and we assume this density independent reproduction, the way that the population grows is geometrically. And if we consider that R0 is equal to e to the power of r, then we recover the exponential growth. So this kind of density independent map, or this kind of density independent growth rate is the discrete in time equivalent to the exponential growth that we saw before. Another way to see that is by, of course, we are more than welcome to do a graphical representation of how these population sizes change in time. So, for instance, if we start with 1 individual, and let's say we are taking R0, let me put this here, and we are taking R0 equal to 2, this means that in time equal to 1, I am going to have 2 individuals. Yeah, right? I only have to say 1 times R0 to the power of t, which is 2. And then I am going to drag this through time 2, 3, 4, and probably I won't have a space for more. So this will be in time 2 would be 4, and then it will be something like 8 here. So you guys can connect the dots, and you will see that this is how our population size looks as a function of time. Of course, I am using dashed lines because in principle, my reproductions happen in the same time, and I would need to do something like this, right? If I were, I did something wrong. Right? Between a whole year, nothing happens. And then all of a sudden I have a jump. Nothing happens. And then I have another jump, and so on and so forth. It's almost trivial to work the case where R is smaller than 1. For instance, R is equal to 1/2. You can work the case and you can do the plot, and you will see that it's pretty much the same. It's just evaluating an iterative function. So far there is nothing especially hard in this kind of models, but there will be, and because there will be, there is ways to analyze these models that are going to be extremely helpful. And the one that we're going to use a lot, and you will see in 15 minutes how really important it is, this approach to study discrete in time models, is what is called the cobweb analysis. So the cobweb analysis is a way to study these models where we are going to follow 2 steps. So first of all, we are going to draw our axis. Perfect. Let's do it well. And then I am going to plot in the y-axis. I'm going to have n at time t plus 1, and here I'm going to plot n. I'm going to put nt. Okay. Now what I am going to do is I am going to write the line. Let's see, how can I do this so it is clear with red. I am going to draw a line that has a slope 1. This line with a slope 1 would be the line over which my population would stay if the number of individuals at time t plus 1 were always equal to the number of individuals at time t, okay? And now I am going to consider my density independent model that we said was nt plus 1 is equal to R0 nt. And I am going to, basically what I have in my axis, I am going to represent nt0 in the y-axis, and then in the x-axis, I'm going to plot this function, basically, speaking clearly. So if nt is equal to 0, this is going to be equal to 0. So these two lines are going to start from the same point. Now, if R0 is larger than 1, the slope of this line is going to be larger than the slope of the red line, and if R0 is smaller than 1, the slope is going to be weaker, okay? So we are going to follow up with the case that we studied before with the iteration of the map, and we are going to consider R larger than 1. So a line that would look something like this, okay. This here would be R0 nt, and this would be N, let's use red, nt. And now what I'm going to do, I'm going to start with my initial population size. Let's say I take N0, okay? And this is t equal to 0. Now, between time 0 and time 1, what is happening in the system? If we look at this is time 0, and this is going to be time 1. In between both, nothing happens, right? So what I am going to do is I'm going to say, okay, so now, and I'm going to use, I don't know which color you guys like, green. From time 0 to time 1, I'm going to, nothing happens. So basically this means that I go to the 1-1 line. Now I am right in the moment before my insects hatch, right in that precise moment before. I have the same animals, the same number of animals or individuals I had in 2020, but in 3 seconds I'm going to have the reproduction event. Once that reproduction event happens, where should I go? I should go up, right? And then I have the same. I have another time where I don't have reproduction. I go back here. I go up, here, up, and so on and so forth. So basically, this would be in time 1, in time 2, and so on and so forth. So what can I do with this graphical analysis is a way in which, without iterating my map, I am able to follow the dynamics. You guys can see here already that this is going to go to infinity. Every time my population is larger, larger, and larger. This, of course, in this case, it's not very helpful, or doesn't provide us with a lot of benefits compared to iterating the map. I agree with you, but let's see what happens if we have a situation that is a little bit more complicated. And I'm not going to put something extremely complicated. I'm just going to imagine a situation where I have the same reproduction that is density independent. But now, for any reason, I have immigration. What do I mean by immigration? Well, what probably you guys are imagining. What I did when I came to Brazil. I have a series of insects that are arriving to the island where I'm measuring my population size. So I don't only have reproduction. My crickets are not only hatching themselves, but I don't know, I also have some of them that hatch in another place and fly to find resources in my environment because it's more profitable for them, or because there is more competition in another place, or something like that. How can I write that in terms of my equations? Well, I can just say that the number of individuals at time t plus 1 is equal to my reproduction contribution plus some immigration that I am going to label with delta. Delta is going to be the mean number of insects, the mean number of individuals that arrive to my environment every year or every generation. Okay, I'm using year as an abuse of language. The proper term is generation. That's why I use 1, because it does not depend how many years it is, it's 1 generation. In this case, we still can solve this iteration process. And if I want to solve the iteration processes, basically what I have to calculate is when I get some stationary value of individuals in a way that the number of individuals at time t plus 1 is equal to the number of individuals to the reproduction, to the growth rate, basically. Right? At some point, I have a map, I have an iteration, and if I want to calculate when that iteration is going to stop, I have to get a point where the next generation is going to be given by the previous one, basically. This, luckily for us, is still solvable, and I can get this solution. So now, because I have this immigration, basically, if R0 is smaller than 1, I am going to have my population stabilized in some point that is not going to be infinity. Basically, the idea that you guys can get from this is that if I don't have immigration and R0 is smaller than 1, you can repeat this graphical analysis. You would have some line that is behind here, and wherever you start, what you would do is to go from here, from here to here, and then here, 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 here. You invert the direction of the stairs, and you eventually hit 0. When I have immigration, I can see very easily in my graphical analysis. Let's see if we can repeat it quickly. Now I still have my 1, 1 line, nothing changed. But now my blue line when t is equal to 0, it's not 0 anymore. Now it's some delta. And now the slope, R0, we said it was going to be smaller than, is going to be smaller than 1, which means that my slope is going to be, sorry. My slope is going to be something like this. So now, guys, if you start with an initial population N0, and you are here, from here, again, you go to, okay, let's do this one. From here, you go to here, then here, 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 and eventually you stop there. So now you do have a fixed point of your iterative map. Of course, if R0 is larger than 1, your slope is going to be, well, it's going to be very much larger than the red line, and we won't get this stable point. We won't get to this fixed point, which makes sense because I have the same dynamics that I had before, but now I am adding more. I am adding more and more and more and more individuals to my pool, so then the population is going to exploit much faster. So, especially regarding this cobweb analysis, because it's going to be very important in the next hour. If you guys have any question, I think now is the perfect moment to make it. No? Okay, so as I said, this is super simple, but it's as simple as the exponential growth. and therefore it's as unrealistic as the exponential growth. So that's why I said in the beginning that we were going to study this compensation and overcompensation models. So what do I mean by compensation and overcompensation? What I mean is that if I plot my let's put this down. If I plot the ratio between nt plus 1 and nt as a function of nt, which means how fast the population grows, the relative growth of the population as a function of the number of individuals in the population. For the case that we studied before, this density independent case, as its name is already telling us, if nt plus 1 is equal to R0 nt, this means that nt plus 1 over nt is equal to R0. So it doesn't matter how many individuals I have, I always leave behind, on average, R0 offspring, which is what we already discussed. So what do I mean by compensation? What I mean by compensation is that somehow I'm going to introduce intra-specific interactions, intra-specific competition. So what I'm going to introduce is an additional interaction, an additional mechanism in my model that is going to make this growth rate to decelerate as the number of individuals increases. Okay, this is going to be compensation. And we're going to put mathematical forms for this. So don't worry at this moment. And what do I mean by overcompensation? By overcompensation, I mean an extreme way of compensation that basically is going to make my relative growth rate to decelerate and to hit zero at some point. If this is not very clear for you guys, looking at this picture, you can also, that maybe it's more clear, an alternative way to look at this is by representing the nt plus 1, nt, is by representing the growth rate of the population as a function of the population size, as we did for the differential equations. So in the case of compensation, what we are going to have is that if we still plot here the one-to-one line, what we are going to have is that the growth rate is going to increase and eventually is going to saturate to some value. Okay. For overcompensation, what we are going to have is an even more extreme way of autoregulation that is going to make this growth rate to increase, reach a maximum, and then eventually go to zero. So in one case, this is compensation, and this is overcompensation. In one case, the self-regulation of the population growth is going to be intense enough to stop the growth, but still there will be some individuals that will get the amount of resources necessary to reproduce, if you want. In the other case, it's more like for those of you that have read something about that, I don't know, game theory or things like that, it's more kind of a tragedy of the commons in the sense that people are fighting. Imagine that, I don't know, there are some finite resources, they are fighting for them, each of them gets, I don't know, a proportional part of the resources, but that's not, imagine, I don't know, that you have 10 apples, and if you want to reproduce, because you are an insect, you need 5 apples. In this case here, what we are saying is that if we have 10 insects, 2 of them will get 5 apples, and the other 8 are getting nothing. So the 2 that get 5, they reproduce, and the others don't. But there's still some reproduction. In this overcompensation case, what we are saying is that each of the insects gets 1 apple, and because no one gets the minimum amount of food to reproduce, no one reproduces. Okay, that's the idea between these 2 different types of self-regulation in the growth of the populations. Both of them happen in different systems, both of them represent a different way of interaction, and both of them are equally realistic. The only thing is knowing which one is the one that represents the system that you will eventually study. But both are equally wrong and equally right. Wrong in the sense that both are simplifications, and right in the sense that they still give us some intuition. So what I suggest now is that we are going to start with this compensation, because it's one that is, I'm not going to say less fun, but it's definitely less beauty and easier to follow. So let's start with that one, and then we will go to the overcompensation one that I am hoping will make you think a lot tonight. So I'm expecting a lot of emails today. So let's take this compensation case. I'm going to copy it, and I am going to take it to the next page. Okay. So this is very nice. I put the figure here. You have this nice plot, but we need an actual mathematical shape or mathematical form for our model. So the one that we are going to use, I'm going to give you also the name, but just let me copy the form, which is not very intuitive. Okay, this is, I have the name here. Sorry, you see? Yes, is this Beverton-Holt curve. It's the name of the people that developed it. And the reason why we are going to use this form, despite not being extremely intuitive or pretty, is because we will see that it's the equivalent of the logistic model to the equivalent of the logistic model in discrete time. That's why we take this. We will see that the shape of the curve is the same and everything is the same. So that's why this specific shape of the map is so interesting. So let's put a square here. So there are many things we can do. To this map. We can calculate the fixed points as we did before. So we can calculate one if we say that this is equal to n t plus 1 is equal to sum f n t. We can calculate the fixed points as we did before, and you will see that we have 2 fixed points. The first one is n star equal to 0, and the second one is equal to k, which already gives us an idea of these connections with the logistic model. We have a carrying capacity here. We can calculate the stability of these points, although there is some subtle differences between the stability in differential equations and the stability in difference equations. So very quickly, the thing that we need to do to calculate the stability is we need to define perturbations around the stationary state, the stationary state, in a way that we basically say that we move a little bit around. This is pretty much the same we did before. And now we can, we can write our equation. This would be nt plus 1, and this would be equal to some function f an asterisk plus n star. Okay, we can do the same that we did before. We do a Taylor expansion on this. Plus higher order terms in the perturbation. And basically this and this, they vanish because this is now the condition for the fixed point. And basically what we get is an iterative equation for the map. This is basically the density independent map or the density independent model we saw before, right? If I just say nt plus 1 is equal to R0 nt, is the same, but instead of having nt, I have the perturbations. And we already saw that this is going to diverge if R0 is larger than 1, or it's going to go to 0 if R0 is smaller than 1. So basically the stability conditions now are that if the derivative of the function f is smaller than 1, the fixed point is stable, and if it is larger than 1, it's unstable. This is just because now we have discrete time and the growth is geometric. So basically we need to do this change in which R0 is equal to the exponential of R, and you recover all the conditions. But it is important that now is 1 instead of 0 in the sense of working the stability. If you guys impose it to be equal to 0, you will get to wrong results and you get a lot of confusion. So this is a side note to calculate the stability of these points. Of course, if the derivative is equal to 1, there is nothing I can say about the stability of the point from the linear in the linear term, as always in these cases. So if we go now to our map, let's copy this, put it here. We can calculate f prime. That is going to be like this. You can do the calculation, it's not very hard. And basically from this derivative here, what we get is that if n star equal to 0, then the f prime of 0 is equal to R0. So it's unstable if R0 is larger than 1. Let's put here 4 rather than if. For n star equal to k, we can do the same, and you guys will get that this is equal to 1 over R0, and therefore n equal to k is stable if R0 is larger. Which makes sense, because if we have two fixed points, as we said for the differential equation case, and one is stable, unstable, the other one needs to be stable. So basically, what this analysis is telling us is that if we start this map with a very, very small perturbation around 0, and we do all the iterations, eventually we will reach a current capacity. And because now I think it's it's complex enough for me to not be able to draw it clearly with my hands. This is what you guys would get. For instance, if you start your population size with some small value and you get R0 larger than 1, you will get through the iterations that the population starts growing, and eventually compensation comes into play, and the population saturates at K, which is the value that I chose here. Here I'm using K equal to 10. If I choose an R0 that is very small, then the iteration takes me to 0, to 0, to 0, and eventually my population goes extinct. How does this look in the cobweb analysis that we drew before? So you can see that for the red line, basically this blue point is my initial condition, and eventually I will heat up, then go to the 1-to-1 line, up, 1-to-1, up, 1-to-1, and eventually I will go to the current capacity, which is the system that I have here. Here it is not so clear because I wanted to use the same initial condition, and kind of the scale is terrible to observe this, but basically what you have is the opposite direction in the stairs. So more clearly, this is the same model, but with a different R0 value. And here you guys see what I was trying to explain before. I start with some initial population size that I think in this case I chose 8. I have 8 individuals. Then I go to the 1-to-1 line and I hit down 1-to-1, down, 1-to-1, down, and eventually I go to 0. And if I go with a different R0, it's the same that I showed you guys before, but with a more clear scale. So remember that the only thing is that this line, this red line here, is basically f of n t. So I always plot my growth rate, and then I plot the 1-to-1 line. So there are very few notes, final notes I want to make about this map before we go to the final map that I want to discuss. The first one is that this is one of the very few discrete or difference equations or nonlinear difference equations that we can solve analytically. So in Mark, I think it's Mark Cott. Mark is his name? Yes. In Mark Cott's book, he has a book that is called Mathematical Ecology. And I think he discusses how to get the analytical solution for this model, how to recover the logistic equation, the exact solution for the logistic equation if you change times from discrete to continuous, and it's easy to follow. He's not extremely rigorous on mathematical. I recommend you a lot that book if you guys want to learn mathematical ecology without learning a lot of math and just getting intuition. That's a very, very interesting book. The other thing that I think is interesting is that this model, and I already said that many times, but I think it's important to remember that is that this model accounts for some kind of cell regulation in the population size. But notice that despite the model having the same behavior as the logistic model, the logistic equation, the growth rate is very different. The form of this right height sign of the equation is very different as well. So I don't know, very naively I would say, okay, if I want to recover the logistic limit, if I want to study the discrete time version of the logistic model, I want to get the same dynamics. What I would do is something like this. Right? Why not? I mean, why do I need to go to this complicated thing if I want to study a model that I know behaves has this form in the continuous time, and I can discretize time. And this is what I want to discuss the last half an hour of today's lecture. I want to discuss with you how this model behaves. And you will see that this model, despite being extremely simple, is one of the models with more complex and rich behaviors you can find out there. It's extremely complex, the behavior that it has. So the way we are going to derive it, and this is, sorry, the case of overcompensation. So the way that we are going to derive it, we are going to start from the time derivative in population size. This is continuous time, logistic model. And I am going to discretize the derivative. I'm going to say, okay, this is nt plus 1 minus nt over some delta t, and this is going to be rnt 1 minus nt over k. Because I am working with generations, I can say that this is equal to 1. That's not a very big deal. And then I can say, okay, nt plus 1 is equal to nt plus rnt 1 minus nt. So this is the discrete time version of the logistic equation, the logistic model for indifferential equations. In Mark Cott's book also, or this is Jim Morris, in Mark Cott's book, chapter 4, they studied this version with dimensions. They studied this model. What I'm going to discuss is the non-dimensional version of this model that has exactly the same behavior, but has more, it's shorter to write. It's basically, you can renormalize the time as we did yesterday. We can work in units of the current capacity, and basically the non-dimensional form, I'm going to use x is mu xt 1 minus xt. I want to say once more that I am taking the right to be a bit more mathematical now. I'm working with an expression that is mathematically more convenient. The behavior that we get is the same. The only thing that will change is that, of course, now I'm going to use mu as my parameter control. And if you don't do this non-dimensionalization, you probably will have some r plus 1 here that will come from nt and nt here. Other than that, it's the same. You will get the same transitions. You will only need to be careful on when they happen. But it's pretty much the same. What is very interesting about this non-dimensional version of this map is that it is if mu is smaller than 4, it is self-contained in the dynamics. Is self-contained. Dynamics is such that, let's say, it's such that x is always between 0 and 1. And I think I can put closed. Now I don't remember. So this is very interesting. It's a map that goes from any number between 0 and 1 to another number between 0 and 1. I always work bounded in this interval. If you guys get a mu, put a mu that is larger than 1, larger than 4, then that property is not so, you lose that property basically, and the behavior of the model is not so good. So we're going to use mu always smaller than 4. Sorry. And we are going to also use mu positive. So what can we do to this? What can we do to this equation now? What do you guys want to do first? No one wants to calculate the fixed points? Okay.
That's what I was.
Fixed points. So what are the fixed points of this model? I have to do I have to solve this equation. Basically, it means that the first fixed point is equal to 0. And in the second case, I will get that x I will get that 1 is equal to mu 1 minus x star. So basically 1 minus mu is going to be, sorry, mu minus 1 is going to be 1 minus x star. So basically x star is going to be 1 minus mu minus 1. These are the two fixed points that I have. The next thing that probably you guys want to do is to calculate the stability of the points. How do I calculate the stability? I just need to calculate the derivative of fxt, and that's it's going to be mu 1 minus 2xt. This is going to be f prime of xt. So if I want to calculate the stability of x star equal to 0, basically f prime at 0 is equal to mu. So if mu is smaller than 1, x star equal to 0 is stable. Everyone agrees with that? Okay. If mu is bigger than 1, then the x star equal to 0 is an unstable fixed point. But we have another fixed point, which is 1 minus mu minus 1. F prime of 1 minus mu minus 1 is equal to mu 1 minus 2 minus 2 minus mu minus 1. And this is basically 2 minus mu. Let's skip all the algebra and 2 minus mu. So if, who wants to tell me the conditions of stability of this fixed point? So I can drink a bit of water, that I have my throat a bit. When is this smaller than 1? No one? Okay. Not even in the chat. So if mu is larger, if mu is smaller than 3, right? This here. So basically, if mu is equal to 3, this is equal to minus 1. So if mu is larger than 3, then this is larger than minus 1, and then the point is unstable. Everyone agrees with me? Oof. And if mu is larger than 1, this here is smaller than 1 as well. So basically, if mu is smaller than 3 and larger than 1, the fixed point is stable. Everyone agrees with me with that? Okay. So what does this mean? This means that and now we are going to discuss everything in terms of figures. This means that if I allow this model to iterate many times, a million times, and I plot here that value of x, or let's say, let's explain it this way. I'm going to take x of t and I am going to iterate it so over many time steps. I don't know, 1,000,000 time steps. And from that 1,000,000 time steps, I'm going to take the last 10,000. So I am going to avoid any long transient, and I am going to take a bunch of points in the stationary state. And I am going to represent those points here as a function of mu. If mu is smaller than 1, all those 1,000 points that I will get are going to be 0, right? So what you guys cannot see here is 1,000 zeros, 1,000 points, 1,000, 1,000, 1,000, 1,000, 1,000. If I now go to mu that is larger than 1, and I repeat the same thing, what I will get is again 1,000 points with the same value, but now the value is going to be 1 minus mu minus 1, which is the second stationary point. That's what you guys have here, here, until mu is equal to 3. Now the question is, what happens when mu is equal to 3? How is the stability of that point going to change? And the answer, and I'm going to recommend you a reading after we finish today, the answer is that the behavior of this model becomes extremely rich and extremely complex. So what I have to here for to show you is basically the I don't know why this is not working anymore. Some analysis I did of this model. So let's explain it very carefully. So this is the first situation that I was describing you guys, the one that you have in the screen. What I'm going to show you is in the left, the time series of the iteration. I am going to start with NT equal to, for instance, 0.8, and I am going to do some iterations, and I am going to see how this is going. And what I am showing you here in the right is the cobweb analysis of this situation. Remember, the dashed line is the one-to-one line, so slope 1. I am using a domain that goes from 1 to 0 because my map is self-contained in 1, 0. And then in red, I am always going to show you the parabolic, the overcompensation growth rate, if you want. So mu x 1 minus x. As you guys can already see, as I play with mu, I am going to change the shape of that parabola. And that is going to be the key point in this model. The shape of this parabola is going to be the key point in this model. Why? Because, for instance, when mu is smaller than, I'm sorry, all this is mu. I didn't decide until the last moment if I was going to use mu or r, and then I didn't change. So if mu is smaller than 1, the slope close to 0 is going to be smaller for the parabola than for the line. You can do, you can see that by expanding in Taylor the parabola if you want, or if you know graphical analysis by plotting these figures. So if I start with x equal to 0.8, which is this point here, remember that the only thing I have to go, I go to the growth rate, and then I go to the one-to-one line. Then I go back to the growth rate, one-to-one, growth rate, one-to-one, and eventually go to 0. This is nothing too different to, I don't know, any of the models that we saw before. Even for the model with R0 smaller than 1, we would have something like this. It would be the same, because at the end, I don't have any crossing point. So nothing very interesting. The funny thing happens as we increase mu. So here for a larger mu, you already see that mu is now larger than 1, which means that the slope here is more a step for the parabola than for the line. So therefore, I will always have a crossing point. This crossing point, which will be the second fixed point that we calculated, is going to be stable. And you can see that by starting from a very tiny population. Here, I think I put like something like 10 to the power of -4 or something like that. And you see that it will grow, 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 and it will reach the current capacity. If you zoom in here, you will see that in the beginning we have this growth, and then eventually we hit the stationary state. So this is very similar to the compensation case, right? Nothing fascinating so far. Okay, now the parabola is going down, but I'm not reaching that part. So who cares? Maybe if you start here, you will see something different, but qualitatively, which is what we like, where we like to find differences, there is nothing happening. But let's see what happens if we take our smaller, sorry, if we take our approach into 3, but still in 3, it's still smaller than 3, sorry. What you guys will see if you iterate your map, and I am starting from the same initial condition, is that eventually you will grow, you will outgrow the current capacity, and then you will have damped oscillations until you reach the stationary state. If you repeat the cobweb analysis, you will see that you will do these stairs, and then eventually you will get into these spirals that will basically end up hitting the fixed point. This is already, I would say it's already pretty enough, but still not very surprising. I mean, we got this in two-dimensional models in continuous time. We saw the conditions for them for this oscillation to appear before. Now we have them in one dimension, but okay, it's not very interest or not very surprising if you want. But now I am going to go to mu larger than 3.25. In this case, you can iterate your map, and you can do this with a calculator if you want, or with your hands. It's not super hard. And what you will get is that the system will show these oscillations, but these oscillations will not decay. They will be maintained in time. What does it mean? It means if I do my cobweb analysis, I will start also from a very small population. I will do the same stairs up to my approach, my fixed point, but then eventually I will, these spirals or square spirals, instead of going to the fixed point, they will get trapped into a square that is going to be stationary. So what I am showing you guys here in the right panel is a representation of, I think, the iteration from 100 to 200. And you see that I cannot distinguish them, that my system will go from here to the one-to-one line, from here to the growth, one-to-one growth, one-to-one growth, one-to-one. And this is happening because you can understand this just with geometric arguments. So the way that the parabola, the shape that the parabola has compared to the one-to-one slope, the slope of the one-to-one line is such that I always hit the same 2 points in the parabola. So if you guys, I think I didn't represent it. Okay, so we can move it. So if you guys now want to make a bigger zoom here in 3.25, and remember that we are going to run our model for 1,000,000 time steps, and we are going to grab 10,000. What are you going to see? You are going to see 5,000 points here and 5,000 points here. As you change R, I will show you the full plot afterwards. As you decrease R, you will see that what we have is what is called a period doubling bifurcation, where basically our system goes from having only one fixed point to having oscillations between two of them. But let's keep playing with mu. If now I take, and this is again mu, if now I take mu equal to 3.5, and I do my time series, you see that now the time series has a different period. So you already see here that I am jumping between 4 values. And I repeat, I have a period 4. Instead of 2, I have a period 4. This means that if I do my cobweb analysis, where I am again representing these trajectories in this kind of scheme that we develop, I again approximate the stationary state, the fixed point, and then eventually I have these spirals. And now, instead of stabilizing in hitting 2 points in the parabola, they stabilize in hitting 4. And here I am again I am showing you 100 realizations of the model. It is not that I'm showing you 4. There is a lot, but they are identical. This is periodic. So if I come here to 3.5, I will get 4 different values. Even if I collect 2 million points, I have 4 different values because it's a periodic solution. So who wants to bet what happens? Sorry, I don't know by heart where this, how many figures I put. Who wants to bet what's going to happen if I go above 3.5? Anyone wants to say something? Sorry, I need more water today. I am very bad with the throat.
Eight cycles, like 8 points for the cycle.
If I go above 3.5, I will get 8 points, which unfortunately I didn't include it here. That's why I was going a bit forward to see if I had. I don't have it with 8. I put you guys in the Dropbox folder the mathematical notebook where which you can produce all these plots, you can change R, you can see how these things happen. But I am going to show the whole picture now to you. What happens if I go very, very close to 4 is that now I lose all the periodicity of my signal, of my time series. Now I have an erratic sequence where I cannot predict, I cannot find any periodicity. If I give you the exact initial condition, you can tell me what is going to be the 10,000 iteration. If I give you N0 and I give you the map, you can give me N2000, you can give me N3 million. This is not a stochastic because in a stochastic process, remember that you cannot tell me how many cells you will have after 1 year. You can tell me the probability of having a number of cells. Here, it is not the case. Here, if I give you, I tell you, you're going to have x0 equal to 0.01 and xt plus 1 equal to mu xt 1 minus xt. Please give me x 10 to the power of 8. You can tell me. Deterministic. Okay, this is not a stochastic process, but I don't have any periodicity in my system, and you can see it here. Here, it doesn't matter in the cobweb analysis. It doesn't matter how many iterations I show you. You will see that this will eventually this will fill all this space, and you won't have any fixed periodicity. So, as you go through this, as you reach this phase, if you come here to this plot and you put the 1,000 or the 10,000 points that we decided, you are going to have points. In principle, you are going to have points everywhere. And remember that we are getting all these period doubling bifurcations, we are getting all these transitions into chaos, we are getting all this with a map that is this. You can get this kind of behaviors with differential equations. Yes, Lorentz model is the classical example of chaotic behavior in differential equations, but that's a 3-dimensional model. It's a 3-dimensional system. You need 3 ODEs coupled with couple. You need 3 couple ODEs. Here, we only need this difference equation and we get all this behavior. And just to show you how this looks like, if you run this fully, this is like how this bifurcation diagrams that I was building by hand before look like. So again, we have here that 0 is stable, here we have that the other fixed point is unstable, and here we have this sequence of period doublings. Here we have the 8 periods that Andres was mentioning, and I wasn't sure if I was including them. That's period 8, and so on and so forth. So you can have a zoom on it, and you see all the pretty bifurcations. So before I show you something else, I want to know if there is something that takes your attention in this plot here, in this one.
There's a kind of gap in the middle.
Yes, very good. Here, I seem to recover periodicity again, right? This is very weird. Let's see what happens if we do a zoom there. By chance, I don't know. I was also curious about that, and I did a zoom on it. So here, look at what I was showing you, and again, this is mu. I'm showing you a much small window. This is from 3.7 to 3.9, and we have actually more windows of periodicity if you look at them. And now I did some spoiler, so I don't think it makes a lot of sense to ask you, what do you think about this part here? It's not. Can you guys see when I highlight something in the screen, or you can't? Now you can.
It's a bit lagged, but yeah, now I can.
Yes, I think my connection is not very good today. But I was going to ask you if you find something interesting here. But of course, I spoiled myself. So we have this here, we have this here, we have also this here. So if I do a bit more of a zoom, look how small my mu scale is now, 3.84, 3.856. What I get is, of course, it's not the same because the fixed point cannot have the same value, but still I have a single, it's not also single, and I want to clarify that because here I'm making a zoom here, and here I'm just taking this value, but you have more values here, right? So I have periodicity. It's not that I have one fixed point. But the idea is that you still have this period doubling bifurcations, and then you recover again the chaotic behavior of the system. So with this, I'm going to finish. What we have in these bifurcation diagrams that is giving us this logistic map is a fractal structure. So we have, if we zoom in, we have kind of the same, and so on and so forth. So we are not going to discuss fractals in this course, but I think it is either again Mark Cott's book or Jim Murray's, one of the two I gave you the last in the first lecture, that they discuss fractals in a very nice way. They explain how can you construct fractals by iterating geometric structures, how to calculate fractal dimensions, and things like that. If you are interested in that. So with this, we got to the end of the third lecture. I'm going to leave the pretty patterns that we're going to discuss in the next lectures for you to keep coming to the course. And if you guys have any question, I'm more than happy to take them. So please ask. I'm going to stop recording so we have this discussion more intimate.